Good morning, everybody, and welcome to the JKMRC Friday seminars. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians on the land on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australia and the global society. Today, it's my great pleasure to welcome Randolph Pax. Randolph has a PhD in physics, specializing in solid-state physics. After graduating, he joined LISAC, BHP, as a research scientist, where he developed image processing, AI signal processing techniques for the determination of real-time process operations. Before joining the JKMRC in 1998, he had academic interest in Australian universities, aerospace, USA, and the Australian sugar industry. Randolph has specific interest in mathematical modeling of processes and measurements, spectroscopy, and control. While at the JKMRC, he was part of and led projects in mineral sands beneficiation and comminution. He has pioneered the use of non-contact acoustics for the determination of in-mill measurements. Randolph has been running his own business for the last 15 years. Today, he will be talking about some considerations for comminutions of ore. Please join me in welcoming Randolph.
Okay. What you were just seeing was the smart noise system, which I'll be talking about. It runs 100% of the time, don't have silly crashes. And that was real time on site, obviously a video. I've basically done the tech transfer out to sites with multiple installations. So I use this background on this slide to highlight an important point in measurement. It's a very beautiful picture, I hope you agree. And it was a sunset taken by some fellow. And the sun was obviously just over the horizon. So it shed light to the understory of the clouds, giving rise to these features. The point is, by measuring the right way, you can get out some amazing information. And it's really important to think about your measurement instead of just blindly doing what you always do. So, oops. As always, I stand on a lot of shoulders to get to what I've done and so on. And the presentation, I'll introduce a bit of grinding, not very elaborate, and then go through the measurement and acoustic measurement for grinding mills. The bottom photograph of me in my younger days, yes, I did have black hair. Something happened along the way. And that was actually one of the installations where we had 8 microphones and strain gauges all mounted on a mill shell, and it all ran on a 133 Pentium, which some of you probably will ask, what's that? But I'll leave it as an exercise for you to find out what that is, maybe. So, from a perspective, mining is a risky business. So the object of mining is to obtain an element or a mineral because it's useful to Homo sapiens. Okay, we're Homo sapiens, us humans. We want these things so we can have our computers and roads and whatever else you name it, and toys for our kids. The process of mining has to cost less than the market price. The market price is dictated by demand, usefulness, and supply. Think lithium at the moment. It's gone through an enormous peak, and now rare earth minerals are becoming very much in demand, and the price is going up. The risk is due to fluctuations, deviations in the technical and economic issues But we also should bear in mind my last little bullet point is there's a lot of research being done and has been done for a number of decades already in development of competing materials for human endeavors. That particular reference, 2022, is a paper that talks about the chemistry of polymers, highly conductive polymers, okay? So copper and silver won't necessarily be king in the future. And perhaps the demand for those minerals will decrease with time as more and more stuff gets done. If you do a literature search on polymeric materials or advanced polymeric materials, you'll find there's research being done all around the world. Risk mitigation models. One way of mitigating risk, which is also something that I believe we all do here, and is use models. And we try to understand how our unit operations work. We can use them for simulation like SimMet, plant design configuration, and we can use models within control schemes. However, the models are limited by the quality and quantity of the data. If empirical data is used, extrapolation is a dangerous thing. If it's real physical chemical models, then completeness is an issue. So, risk mitigation models. George Box in 1976 came up with this quote, which I'm sure we've all seen. All models are approximations, but some are useful. However, it's not a license to ignore facts. Just because you've got a model that seems to work a good chunk of the time, it doesn't mean that you know it all. Uncertainty is the status quo, and the world doesn't wait for the luxury of complete models. So we need some measurement. The majority of plants have no or limited in-mill measurement, and virtually all measurements are conducted external to the unit operations. Some measurements are gross approximations or lack detail. And in this industry in particular, we rely on a very large number of particles in our processing. So we do what's called averaging, average behavior. Now, averages are a bit dangerous when they're done like that. These measurements can be used within models, and we heard an excellent talk a few weeks ago by one of your people about soft sensing. It's come a long way here at the JK. Mill internal measurements are very challenging. It's a hostile environment, but smart noise tries to address that. So a simple grinding circuit, you've got a mountain, you've got some nice ore in there, and you geologists know more about how to deal with that side of things. It gets blasted. And notice I'm going to put up a set of vertical bars, which are cost per ton, and it's scaled. So the next step is crushing, and the next step is grinding, and there's a DEM calculation, a model, which is an approximation to real life. And you notice first that the grinding cost is much greater than the other two. And in fact, 47%, according to this paper here, which is an old paper, of the energy cost of a mineral processing plant is in the grinding stage. Not very good. So to deal with this, again here at the JK, they were the first to do mine to mill, as in basically balance the blasting cost, which is cheap to do, against the grinding cost, which is much more expensive to do. The other thing you can do is improve measurement. Breakage of rocks is an essential process. Our ancestors worked this out a long time ago, and this is actually a photograph of some stone chips that they found in Indonesia, and they're greater than 1 million years old. They've actually found, other people previously have found stone chips which have obviously been made by Homo or by apes, if you like, our very ancient ancestors. And they had the technique to get these chips because they found them useful, cutting, whatever, poking, but they didn't have the mass. Now, in 1956, Broadbent and Colcott worked out a really nice matrix method for mathematically describing breakage. And in the 60s, Alvin Lynch and the people, early days of JK, adapted it for hard ore breakage, and it's still used today. So, operating conditions in grinding mills. We want optimal breakage rate, liberation, and throughput. The internal mill operating environment for ore breakage is very sensitive to feed ore variability in a mill. You speak to any operator, any metallurgist in the plant, or you play with it yourself, it's crazily sensitive, okay? You can't just hope for the best. It doesn't work that way. It is better, we could use a whole bunch of proxies that are useful, which is what gets done, sorry. Mill load, percent solid stability, power draw, etc., to make an estimate of how the mill is operating. And it gets you there within a 20 to 30% error bar, okay? But it's actually better, in my view, to measure the internal conditions in real time, okay? At least you've got a handle then of what's going on inside. The KPIs are always cost, specific power, stability, and utilization, okay? And I'm sorry, getting used to this silly thing. It's important to make a distinction between SAG, bag, and ball mills, okay? SAG mills were introduced years and years ago, 40, 50 years ago, if not older, to replace rooms full of crushers with recycles, okay? Huge footprint. Very expensive, and maintenance was a nightmare, okay? So SAG mills came along, and they only had 6 to 10% steel ball load, and it was one unit or maybe a couple of units. Capital cost was probably a bit more than one crusher. And then in modern times, people are doing bag mills, barely autogenous grinding, where the steel ball load is around 15%, 20%. I've even heard of 23%. And then there's ball mills at the other extreme. One of the consequences of adding steel balls to mills is that the ability of the mill to handle a top size decreases in terms of the top size. So the top size for a bag mill that it can handle comfortably is significantly less than a SAG mill. It's still better than a ball mill. For a ball mill, people have studied this in great detail. You might have 40 millimeter steel balls, but you can only put in something like 30 millimeter pop size rocks, okay? It's quite significantly less. Unfortunately, people still think of bag mills as a SAG mill, and that causes them strife. Utopia. Wouldn't it be great to be able to determine optimum conditions in real time? The new measurement could also inform new models, new timescales, new frequency content, i.e. dynamics. And ideally, the diagnostics that you can do with this system should be quick because time is money. And I think of production costs or production gross value at roughly 2 million a day for most of the valuable ores that we mine, okay? So instead of spending a month, 2 months, 3 months to work out what a problem is with your circuit, if you can do it in a pleasant afternoon, you saved yourself an absolute fortune. So let's be curious with something new. Let's talk about noise Noise from a mill is not random. It's actually a bunch of mechanisms, and it's an orchestra. Okay, and the algorithms are about picking up those components of the orchestra. The content of the noise depends on the circumferential position of the microphone. And you need particles to interact to generate noise. If I suddenly stop talking in this room and no one moves, you won't hear anything, correct? I start tapping it, and that's what's going on in the mill. It's the balls and the rocks are tapping away. Okay, so noise only listens to that. The toe and shoulder angles that are measured with noise will then not be the same as for strain and vibration measurements. In practice, it actually turns out that the rock toe angle plus the rock steel toe angle divided by 2, take the average, is approximately the same as the strain. And this has been used at one site to get the toe angle out from acoustic measurements, which then can be used in the power model to make an estimate of the loading inside a mill. Interestingly, of course, it's particle interactions that are a requirement for breakage. Okay, and so acoustics has got a twofold advantage. It's external to the mill, so you don't have to get inside the mill, and we're listening to the stuff that actually helps us get breakage inside the mill. That's very powerful. Smart noise has been developed over 29 years plus, with over 70 grinding mills, 20 plus years of real-time operational data at 80 milliseconds per data point. Okay, so a huge quantity of data. I've got hard disks full of this stuff. I've also got the software to analyze it as well. It's gone through many iterations to get to the point where I can do it straightforwardly these days. And it's about algorithm development, and it's provided new insights into how mills operate. It's always been developed from a mineral processing perspective, not an engineering perspective. I feel that a lot of people get it wrong when, especially in companies, when they get an electrical engineer or someone like that who knows their electrical engineering, big tick, to develop something, but they don't know anything about what they're trying to measure. And I think that's a bit of a disaster. You really need to know the other half. You've got to take the time to learn. I always use raw process data. You've heard me comment a couple of weeks ago about that as well, because pi data, for example, has been corrupted. It's not the real stuff anymore. You look at the algorithm that in the pi software for compression. It's actually quite complicated, quite involved, and by the end of it, a lot of information has been destroyed. And so smart noise is more than about media impacting. So the methodology then is collect all the data, okay, including the acoustic data. My data, a row in one of my data files is around 350 data entries, okay? And then the columns are 80 milliseconds apart. So I collect a lot of data, and I'm trying to answer the question, is the mill circuit operating correctly and at its best? And I'm forever looking for events, and there's no shortage of events in a real plant. Looking for causality and other issues. So the smart noise system consists of 2 pieces of software, smart noise and nexus control, together with commercial hardware and communication with the site's DCS to give us process data and also for remote access. And put together a comprehensive implementation and site support / training and documentation, data sheets and white papers. For those of you that don't know what white papers are, they're the discussion documents that tell you a little bit more than the data sheets tell you or anything. So they're more like a research paper, if you like. That's the system there. A mill, 12 microphones, amplifiers. The dotted line indicates what goes out in the field. Occasionally, the field cabinet has to be internally air conditioned. And then there's communication to a computer, one bit for the Nexus control and the other bit for smart noise. And then there's obviously communication to the DCS at the site. With a switched on site team, once the equipment is in place, getting all this comms going and everything is trivial. I mean, it can happen in days. There's also a handheld instrument. I take my laptop and a roving microphone with a little bit of electronics, and I measure along the length of the mill, both sides, and I've got more detail. The numbering convention is the cock face, or mirror of the cock face, an analog cock face, not a digital cock face. Digital doesn't work. That's a microphone in the flesh, as it were, very robust. The failure rate is very low, maybe once per year. I've got, at one site, a few years ago, I had 2.5 years of, it just kept on running. I took one off out of desperation to find out what it was like inside. It was spotless, not a problem. At another site, it's now been running for 8 years, no change of microphones, the same 8 set of microphones. They're very directional. So you've got to allow access for relines. And there's a microphone in place. They get grotty. That's not a problem. Why 12 microphones? Normal competitor systems use 1 or 2 microphones. Some of them say rather cheekily they've got an array of 4 microphones. That means they've got 2 microphones for one direction and another 2 for the other direction. They've really only got 2 microphones operating at any one time. So each microphone has different information content, and at each location there's different impacting mechanisms. The background noise rejection is much better than 60 dB. 60 dB means, with me talking, a pin drop onto this floor, it can still hear that. As in, but it's in the presence of me talking, the software and everything will still hear that pin drop. And in fact, I have done that. I can hear the screeching of the steel balls inside a mill as it's going around, and all sorts of stuff. I can pick up one ball if I wanted to, which I don't, but I have done for curiosity. Simultaneous measurement allows 80 measurements per revolution, per mill, per microphone. 12 microphones also give me a massively increased robustness, reduced uncertainty and confidence of measurement. Because at the end of the day, those 12 microphones have to be connected in logic. What's that logic? Mineral processing, mill operation logic. Okay? Having one measurement doesn't do that. And of course, the acoustic results have to be consistent with the process data. So I do what I call holistic analysis. Just out of interest, I use MATLAB a lot for analysis. Modern MATLAB on a nice fast computer works pretty well. And there's some really nice features in there to let you do anything. In fact, all the maths that you ever learned and didn't learn is in MATLAB, which is really nice. It's a powerful tool for analyzing mills. The steel signal is a really important one. I spent a lot of time trying to get it right, okay? Because I'm looking at the media, especially in SAG and bag mills and ball mills. In ag mills, I've got a rock signal. I've got a rock signal for SAG mills as well, but it's not as useful as it is in an ag mill, which is only rocks, of course. And the steel signal determines only the steel interaction between steel objects in the mill. Okay, how have I tested this? One of the early tests was using it on an ag mill, a rubber-lined ag mill, no less. And the signal went to 0. It wasn't there. Okay, so that's really nice. And then I've had other confirmations as well. Okay, so when in the ideal situation of rocks and media in a mill interacting strongly, the steel media, the steel signal is at a minimum. It's not 0, but it's a minimum. Okay, if there's not enough rocks in the mill, the media interact a little bit more. And if there's no rocks, the steel signals go through the roof. That's a grind out. Okay, and I really mean through the roof. Typical numbers, maybe my units 1. This through the roof signal, 10,000. Very sensitive. So as a consequence, we provide a range of signals, and we've got outlier detection. Okay, detected bits of lifters inside mills. Okay, it works rather well for that. And other bits of crap that come in on the conveyor belt. Okay. The smart noise measurements are, at each microphone, I measure a range of signals, including the steel signal, a rock signal, and impacting signal. And the other thing is, which is what that red dotted line says, it's only on the mill shelf, okay? It's tuned up so that I'm only listening to close to the mill shelf, okay? I should point out, because there's a bunch of geologists here, the stuff that seismologists, geophysicists do with the earthquake detection and whatever else, there's a lot to be learnt there. Okay, normal high-speed impacting or normal speed impacting. There's also something which is one of the new results is top space. Now those DEM calculations, life trajectory calculations, etc., say that doesn't. That shouldn't be happening. Well, it's not true. It does happen. And there's good reasons for happening. And it's basically a billiard table in the top half of the mill. I measure shoulder angles and toe angles. I measure the bull to rock ratio at that microphone. I also measure the water to slurry hold up. Marco, notice my little thing there. I know that's wrong, that picture is wrong, but this diagram is for illustration only. I have load measurements, which are integrated area, ball to rock ratio, holistic load, which I'll come to. The holistic load uses basically all 12 microphones. So it's an all acoustic load measurement. And these signals can be used for all sorts of control aspects as well, to provide, and it's used to provide a logical, self-consistent diagnostic picture of a mill. So much so that when a system first starts up, it's all been installed, I switch it on, have a look at the thing, I immediately pick up a few points that are important for the site, for their grinding mill that they weren't aware of. And this has happened all the time. You saw before the beginning, before this presentation, an interface, the smart noise interface. And this is just a summary. The only bits I really use is these last two bits, which is a summary of the acoustic outputs. And of course, I want to see if the mill is running and it's percent critical. The real speed not really is important, but the more useful number is the percent critical. And there's all this diagnostics over here to tell me whether the system is functioning properly or not. The other thing that's possible with this software is the time scales on the process data and the acoustic data can be made exactly the same, 44 minutes. And so you can compare like with like. In this particular case, just to illustrate the power of it, here's the scats rate or pebble generation, and we can see the toe angle being influenced by the scats. Obviously, there's internal stuff going on that's influencing the steel shoulder angle. Here's a little experiment where we unloaded a mill and then loaded it up again. And the blue line is load cell values. And the green line is the steel signal. And the thing that really strikes you with this data is that the steel signal basically saturates before the load cell values. Okay, in other words, the rock are in between the steel balls, but they cannot take this, the steel balls can't capture any more rocks in their midst. But the rocks are still piling in. And so essentially you end up with an extra phase. So another revelation is these mills can operate and get to the point where there's two phases in the mill, a steel plus rock and a rock only. Here's another validation point, ball to rock ratio, using crash stop data, as in opening the mill and measuring and coming up with what the load is inside the mill versus the steel signal. And we see quite large errors. It's not something this industry talks about very much, is error bars. But the error bars on the crash stop data are much larger than on the steel signal. Okay, and that's an acceptable correlation. We also did a test where a bulldozer put in very large rocks into the mill, and they didn't integrate with the steel balls very well. And that shows up here as a data point that doesn't fit on that other correlation. Okay, it's a nice validation point of the steel signal and that we're actually measuring real mineral processing stuff inside the mill. These are the trajectory calculations that this is my version. And these calculations suggest that steel balls do not occur up around here. I don't know why it does that. Up around here, where in actual fact they do. Okay. One thing that differentiates my calculation from what I believe other people do is I've got viscosity in here, rheology. Okay, and as you would expect, the outer trace on this band of steel balls, and I use a range of steel balls consistent with normal steel ball sizing, if you like. And it's the lighter balls, the smaller balls that fly a bit higher. Now, the funny thing is, when you play with this data, it's almost impossible with speed or anything, reasonable speed or anything, to get steel balls flying up at the 180-degree mark there. Okay, it just doesn't work. These machines are very synchronous. They're quite nice, actually. So when you use your microphones around the mill, these are the two conventional microphones. You see a lot of activity. I've got the process data. but you're seeing a lot of activity. If we now go to some of the other microphones, including the shoulder space on the right-hand side, there's hitting stuff happening everywhere, okay? And because of their directionality of the microphones, you've got unique measurements, okay? And the stuff that's happening on the far side of the mill compared to where you're measuring with a microphone, it's just not hearing that. It's down in the noise. This is stuff happening at each location. And you can do a 3D version of the impacting around the mill, and you're seeing impacting in the top space. You're seeing conventional impacting. There's to even get a steel ball going to 3 o'clock, you need special conditions. The code for the trajectory thing, I was on site and it suddenly hit me that something was amiss. Why am I hearing things at 3 o'clock? So I wrote my own code, spent a day doing it, getting it working, all in MATLAB, and did what I just explained to you. A much more powerful way of presenting this data is like so. Here we've got microphone position. I see, if I keep it down, it does more screens. I see, I get it. On the right-hand side, you're seeing impacting at virtually every position, including the top space. But notice this discontinuity at 6 o'clock, okay? Because that's where the gravity is supporting the charge going down. And on the other side, gravity is not supporting the charge going down. The lifters are doing the work. In contrast, for a polymet lined mill, similar size, they got real problems, okay? They should be getting what I'm showing on the right-hand side, but they've got balls flying everywhere. And there's even some structure here, which I won't go into, which is stuff going on in the shoulder space. Okay, factors affecting media impacting. Well, speed, everyone knows about speed. I'm always at pains to explain to people, rheology is really important, okay? If it gets really sticky, and it does get really sticky up there in the shoulder space, then you're not going to delay steel balls leaving the lifters. Or particle size, maybe shape, because it pins the balls onto the lifters. A fellow called Royson published a lot of papers in the noughties about this stuff. And then large rocks coming into a mill provoke charge agitation, and that means steel balls start flying. If you question what I've just said, have a look at a stockpile, a feed belt onto a stockpile, and as the rocks are coming on top of the stockpile, you'll see particles flying off on the top of the stockpile. That's what's happening inside the mill. The other thing is, I can do some spectroscopy, okay? I've inverted it and called it time of flight measurement of steel balls from each lifter. So I'm seeing the population distribution of media flying from lifters by the height of each of these peaks. This last one is significant. It's a ricochet. It's where a steel ball flies above the toe and then bounces back into the charge. It takes a longer time, okay? And I've had a recent discussion with Paul Cleary, who's in my book is the guru of DEM. And he actually asked me whether I see that. And I said, yes, I do. It shows up very obviously. And he says, why don't people, the mills, encourage a little bit of that? Because you actually end up having more energy for impact. a validation, if we understand the spectroscopy a little bit, then I can see the signals for the top space collisions. They're very short duration. And here's a very pronounced peak of a range of top space collisions. Right, but hurry up. Okay, with multiple microphones, if I've got 4 tow microphones, then instead of using one microphone, say at 4 o'clock, to measure the impacting on the mill shell, it occurred to me that it would be smarter to come up with a metric that uses all 4 microphones in the tow space. So that little formula that I've got written up here is I add up the impacting at microphone 3 and microphone 4 and divide at an instant of time and divide it by all the impacts in microphones 3 to 6. Okay, and that gives me a fairly robust, a much more robust measure of impacting, okay, in the tow space. Here's an example of it's lots of hitting happening above the toe, and this is a much better signal. In the ideal world, this would be, the numbers are between 0 and 1. In the ideal world, this number would be way down here. The reality, it doesn't quite work that way for all the other impacting mechanisms. I've also got a water hold-up signal, which on some slides, you'll see the word equality, same thing. And it's a value that it measures it uses a number of microphones around the mill and then does some signal processing with it. And it's a measure of water hold-up and fines, as in fine material that has been generated in the mill. It's very hard to separate the two. Not that it really matters, but it's a value in the range from 0 to 1. Normal operation I found it to be between 0.1 and 0.4. It indicates the slurry buildup inside the mill and indicates fine generation. And it also is influenced by the feed oil characteristics. Now, the indicates fine generation. At one site, we were playing around with trying to get more throughput through the mill. And we could see, using this signal, we could see when grinding was getting more efficient inside the mill, because suddenly the water hold-up signal went up and stayed there. It was still within the range, but it just went up. And so we played a little bit more to confirm and validate, and it was a treat to see. And I believe that's still the first time anyone has ever measured grinding happening inside a mill in real time without models. Okay, here's some scanning data. Actually, I'm running out of time. So basically, the next 3 slides are showing how the water holdup varies with position of an array. This was a really nice installation, and they did it. I didn't ask for it, where they provided a stepper motor drive for a set of microphones to sweep the length of the mill backwards and forwards. And we could do that in 6 seconds. And as a physicist, I thought, you beauty, let's have some fun. And so I did, and got these sort of results, which shows that the water holdup, for example, is located, most of the water, or a lot of water is located at the feed end of the mill. And then the RMS signal, or the noise level signal, it changes a bit, but it's not very stark. The next interesting one is the steel signal, which is showing that the steel balls are interacting a lot more at the feed end than at the discharge end. That shouldn't surprise us now, because at the feed end, you're feeding in the rocks, okay, large rocks, and so disrupting the charge, okay, and the steel balls basically start clanging together. This is a comparison of my integrated area signal, which is a proxy load, divided, comparing it to the load signal is measured by load cells. And you can see it trends pretty well. Okay, it's certainly within the 30% error bar that's okay in this industry. Here's an interface showing very extreme behavior in this yellow steel signal at the 3 and 4 o'clock microphones. And that's definitely not okay. So just by looking at a graph like this, of the internal measurements, you can tell the mill isn't doing very well. And oftentimes when you see this stuff and you look at the process data, whoa, nice stable throughput, nice stable load, whatever, okay? Internally, the mill is doing crazy stuff. This is another trace of KPIs, or what I call KPIs, which are the toe angles and shoulder angles, water hold up, and integrated area signal. And we notice that the water hold up is actually quite high in this region, and then it drops right down, probably due to a feed disturbance of some sort. And this dotted line here, when the water hold up reaches that thing, you've got a pooling situation. I recall very, very early on, 1998, was relatively new at the JK. A whole team of people had gone up to a site, done measurements, done a survey, analysis. They said the mill was pooling. I went up about a month later with my stuff, and and so this question came up: is it pooling? I did some measurements, and excuse me. Actually, if Tim was here, I would have said something else. I was remembering that movie with a student's phone rang. And do you guys remember this? No. And the student got up, "Oh, it's for you, sir. It's God, it's for you, sir." Sorry. Okay, so, and then while I was there, they finally persuaded the super to open up the mill. And as I was pulling the chute on it, whoosh, it was severely pooling. And that was a nice confirmation for acoustics. It was a nice confirmation for SimMet and all the work that had been done. This is the integrated area. It's actually going very high, so the mill is seriously unloading. But you notice that the water holdup is decreasing every time this is happening. Okay, and that's because when it's unloading, there's no rocks, there's no fines being generated, or not very much. And the water can rush through the matrix of steel balls. Here's another example showing the same thing, simultaneously showing the holistic load doing the correct thing, as in unloading. Integrated area going up means unloading. Here's a nice validation of stuff happening in the shoulder angle, showing up in the toe angle, steel angle. Okay, so that's really nice, the independence, etc. Because the toe angles are small, the integrated area is in a good range, around 2030. Mill loading is okay. I'll skip that one. Just an example, the blue scatter is intermittent packing inside the mill. It's really easy once you measure the shoulder angle to see packing, not a problem. A little aside, at one site, I actually got the project with them because their load cells, they were told, had to be replaced, and they didn't want to do that. So they thought they'd give acoustics a go. And me being me, I got the load cell data, individual data. I did a bit of modeling and so on, and worked out how to correct the load cell data, the 4 outputs from 4 load cells, and ended up with corrected load cell data. And now the load cell reading is the same whether the mill is running or not. For those of us that have been out and seen mills, normally that's not the case, but I've corrected for all the motion and everything else. The other thing that shows up is all the noise that you see on the raw data is basically being wiped out. Okay, so when you do load cell control in a real situation, you're chasing these, whereas you really should be chasing this much slower variation. And that's really, really important. So I mentioned that because in a minute I'm going to compare load cell data with holistic load and so on. So holistic load uses all 12 microphones, a whole bunch of information, and it's set up so 0 is everything's fine. If it's plus greater than 1 about, then it means the mill is heading for overload very sensitively. If it goes negative, then it's heading for underload. And so here's a comparison of holistic load within its band, the sag corrected load cells, showing that when the holistic load goes down, the corrected load cells also go down. I got it. And confirmed by the impacting increasing as the mill is unloading. Here's a comparison of load cell, integrated, 1/over integrated area and bearing pressure. And quite clearly, bearing pressure doesn't work very well. This is great sensitivity, 5 millimeter increase in F80. Comparing the process data, which works out all the correlations that should be there are there. And then we can see, use the acoustic data, and we can see that as we increase the size, we get more power use, we get reduced breakage opportunity, less water in the charge, etc. This is the survey methodology, doing measurements either side of the mill. I find with my height is an advantage because on a 40-foot sag mill, that's 180 degrees or 0. And down there, when I crouch down, is about 200. Okay, so, and that difference makes a big difference. And so here's some data that I get along the length of the mill, equispaced data. And it tells me all sorts of information. The most boring bit is where the feed chute is, or where the feed rocks are coming into the mill, because those rocks are coming in and scattering those steel balls and bingo. And that is the mechanism for getting wear inside a mill as well, unusual wear. As another confirmation, a ball mill, measuring along the length of a ball mill, and at the feed end, everything was fine, coarser material, but when you get in the second half of the mill, I got no hitting events. And at first I thought a wire had come undone on my instrument, but I learned a long time ago that when you think your instrument is faulty, you just keep on going anyway, and then you check afterwards, because you'd hate to lose an opportunity. Okay, and it actually turns out nothing wrong with the instrument. It's due to shape balls, sliding balls. I'll skip this one. It's in a paper, Met Plant 2015. In a couple of hours with acoustic measurement, we took a mill from 850 tons an hour to 1,200 tons an hour and stable. Previously, they couldn't get there. This is variation along the length of the mill. It's changing all the time. There's continual longitudinal movement of mill charge. Solve a whole range of metallurgical issues with the signals, a little bit on control. This is basically speed and throughput control to maintain an acceptable hitting. you know you got it when the only variation, serious variation that you have is in the toe charge angles, toe rock angles. Okay, everything else is basically stable. The little blip in the middle was actually a water disturbance. I won't go through this. One interesting thing that came out, they approached this particular mill, people approached me with, why have we got these wear rings? So I said, okay, let's assume it's steel ball impacting on the feed and discharge ends. And so uploaded all the data for 11 months, calculated self-consistency with trajectory calculations, etc., most likely combinations, and it was still media impact. And this is a consequence of running a mill too well. Okay, you don't want to run the mill too well. If you do, change it a little bit often, because otherwise you get funny wearings. The payback of the system is less than a week. It actually works out to be about 2 days. And this was a 2.5-year project, doing a lot of other stuff as well. It was very quick payback. So the conclusions are that the 12 microphone array is a robust, proven, unique measurement system for real-time internal mills. It's a fast measurement system. Grinding mills are very sensitive to frequent water disturbances. Water holdup indicates grinding in the mill. Rheology of the slurry influences the mill. Particular shoulder mechanisms. A lot of people focus on only the toe, but the shoulder is much more interesting. It's rapid diagnosis, powerful control signals, mill liner protection. That's a boring one. And it enables stable and consistent operation. The overall conclusion is a sentence: non-contact acoustic measurement of mechanisms inside a mill in real time provides the opportunity to adjust mill operating parameters so that all characteristics variability does not detrimentally influence mill operation costs and efficiencies. I'd like to acknowledge all sorts of people in my wanderings around the globe. One year I did 9 months travel, which is too much. So all the guys out there, the people here, and I'd like to particularly thank Rob Morrison when he was the manager of JK Tech, who introduced me to sag milling and converted my thought of, you got to be kidding, this is just steel balls and a tube, to this is much more complicated than that. And I'm still learning about, I'm seeing new stuff in mills all the time. Thank you for listening. My hearing isn't perfect. So
Okay, so thank you. That was very interesting. So as a health and safety person, normally I'm used to seeing noise done from a, what the humans being exposed to perspective. So it's great to see it being used for machine diagnostics as well.
Okay.
Another thing we do with that is I'm seeing the whole body vibration data being used to do predictive analytics for some of the equipment. Have you thought about incorporating the acoustics and the vibration
That's another sub-bit.
together? Could that give
Condition
you,
monitoring of equipment.
yeah,
Right.
any more insights?
It's really hard to persuade the people out there to fund that sort of work,
Okay.
because the people that I've found I'm speaking to are people that know a really great bit of software that helps them schedule maintenance.
Mm.
They don't want to do additional maintenance, or they don't want to do preventative maintenance. In this industry, it's rather bad because they let equipment go to failure, which is crazy.
Yes.
Yep.
Okay.
One last one.
Thank you, Randolph. Brilliant talk. Thank you. I remember 25 years ago, I was sitting in this room and you presented similar stuff when this journey started
long
out.
way.
So it's great stuff. I actually have two questions. I'll ask one. The size of the mill. You've got 12 microphones always. And now if you've got a bigger mill or a smaller mill, the spacing between the microphones change. Does that influence the quality of the signal at all?
These microphones are only listening to an area on the side of the mill about that large, okay? Which means in reality, like, excuse me, I can go from 16 foot and the sky's the limit. And the reason I chose 12 and not 24 or something else, because of that, I would have liked to do more. But it's not worth the effort.
Thank you all for coming and joining us. Please join me again to thank Randolph.
Thank you.
Next week, we have a talk from a professor from McGill University. It will be a webinar only, so please join us next week. Thank you.